Hello, today we are going to start part 3, and here we implement the derivations that we got in part 2 and put them in Python or Google Colab and plot our results and show the transition from stable to unstable results at specific values at the discretization. And to start the code, we want to do what we usually do every time and put the needed libraries that we'll be referencing as we go plotting our results. We want to add in our numerical Python library so that we can compute functions that require more than basic PEMDAS signage. So we start off with writing import numpy as np, and then we have to do our standard imports for plotting out our derivations that we just did. So we will be using Plotly, and that's where we're going to make our subplots function and our plotly.io for the templates. So we write from plotly.subplots import make underscore subplots, and then we will also write import plotly.io as PO. And for the last import, we want something that will help us out with something, help us out with our banded matrix. An banded matrix refers to a matrix that has its non-zero entries confined to a diagonal band and is surrounded by the other two corners with zeros. And luckily, we don't have to try and solve this out on our own, and we can just use SciPy's linear algebra library to solve the banded function. So we're going to write from scipy.lionelg import solve underscore banded. Sorry, there's a fly. And now we will define our variables for the problem. So our number of spatial divisions is going to be nx equals 50. The number of time steps will be nt equals 2000. And then our thermal diffusivity, which is going to be alpha. Note that this is going to be a float, so there will be a decimal point at it. So we have alpha equals 1 point, and the dot is a decimal for the float. And then we have spatial increments, which is also a float number. So we have delta x equals 1 dot as well. And then now we have our time increments, and this is not a float, so we have delta t equals 0.5. And once our variables are defined, we can begin creating our list of spatial positions for plotting. So we're going to start a new code right here, and we end up having x equals np dot arrange, and then in parentheses nx, and then we multiply that by delta x. And after that, we end up having r equals alpha times delta t divided by delta x, and this is squared. So we have 2 asterisks for squared and followed by a 2. And after those are defined, we can set our initial temperature to be uniformly 20 degrees Celsius. Then we're going to set changes in our left and right side temperatures. So on another line, I have t equals np dot full, and then we're going to have that from nx to 20, oops, and add a period because that 20 needs to be a float. So we have t equals numpy dot full, nx 20 dot. And so next we have our left side temperature that will start and stay at 50 degrees Celsius, and this also needs to be a float. So we have t index 0 equals 50 dot. And now for our right side temperature, we have t index -1 equals 80 dot. So now that we have defined all of our variables, we can create our figure to visually represent the transition from stable to unstable. So starting a new line of code, we have fig equals make underscore subplots, and then we have rows equals 1, and then calls equal 1, and those calls are just the columns. And then after this, we have fig.add underscore scatter, and then we have x in parentheses, we have x equals x, y equals capital T, and then we've got name equals in apostrophes initial. And so after this, we need to create a for loop to run our data and plot it in our figure. So on a new line, we have for I in range, and then 1, and then n t plus 1, and then the colon, and underneath that we have t index 1 to -1 equals t index 1 to -1. And then after this, we've got plus r. And then this r is going to be multiplied by index. Oops, sorry. We've got t index 2, and then -2 times t index 1, -1, and then we've got plus t index colon -2. There we go. Whew, all right. Yep, plus t index colon -2 index parentheses. So then we got the end bracket at the end, and now we also begin on a new line, and we have if I percent 100 equals 0. Then after that, we indent again, we have fig.add underscore scatter. And then we've got the same thing that we had above. So I'll just copy this. But then this time, instead of name, we've got mode equals lines, and then name equals F apostrophe, then fancy bracket, I. There we go. And then we have fig.show. So let's run all this. There we go. Okay, numpy.arrange. Let's see what the problem is. Let's just run all these and see. Okay, let's see. Okay, this is supposed to be arrange, not arrange. Okay, there we go. And then I ended up fixing, what was it? This, I was missing a parentheses right here, and then also my index, this had a -1 and it should have been a 2. So let's run all of this from the start. And hopefully we'll get something tangible. All right, so now we have to fix this, we have to make sure this is properly indented. And there we go. I'm going to run all of these, and we should finally get our plots. And there we go. Thank you very much.